about the connection between combinatorics, commutative algebra and Schubert calculus. And I'm told she's been practicing for Amy, but we may need to move forward before we can talk with the whiteboard. So take it away.
Thanks, Avery. I'm told that people may be able to see better if I write on the iPad, so we'll try that out, but please do let me know how things look and sound. And indeed, I did have a helpful conversation yesterday with Alan Knutson, and who's an expert at throwing objects and catching them. And so we'll see if I do better today. I continue to encourage questions. So thank you all for all of your hard work during the exercise sessions and for all of the good questions that you asked. One thing that I learned, I was about to forget again. Sorry, the most important part of the talk, I should introduce my faithful TA, Ada. Could you stand up and wave? Who is a student here at UIUC working with Alex Young. And she has a couple of papers recently out on the archive. And she loves resolutions, and so if you decide to work on the Cohen-Macaulay'ness and resolutions questions, she'll probably be especially happy to be flagged down. So one thing that I learned from people asking questions yesterday during the exercise sessions was that a lot of people would like a review of primary decomposition and associated primes. And so before I get back into the meat of the talk, I want to be sure that we're all on the same page about primes and components. So let's see. So again, we'll let, throughout the talk, S be a polynomial ring over some field K. Let's see. Yeah, for anyone who's just hoping that my handwriting gets better on a white pad, they will be sorely mistaken. And let's let I be a proper ideal of S. Then there exist what are called primary ideals. Q1 to QT, so that I is this intersection of primary ideals. And if you don't know what primary ideals are, the important thing for us is that they're radical as prime. So you can just focus on that feature of them. So if we assume this intersection is irredundant, we can happily do. Then the radical of each of these QI's is PI, and the PI are uniquely determined. There's no choice. We call this set P1 up to PT. The associated primes of S mod I, or sometimes you'll see people write this as the associated primes of I, though I won't. Associated primes come in 3 flavors. So an associated prime, we'll just say, so we'll start with the worst flavor. So not to make value statements about mathematical objects. So a prime in the set is called embedded. If there exists some other prime so that Pj is properly contained in it. So these are the biggest ones. They live above some other associated prime. We don't have these for radical ideals. So these won't come up for us really today, but they exist in life. And then everybody else. So the others, meaning the ones that are minimal with respect to containment, are the minimal primes of S mod I. And we'll denote this min S mod I. Within minimal primes, there are two things that can happen. One is that the height of Pi equals the height of I, and the other is that the height of Pi is greater than the height of I. So as a reminder, we defined the height of a prime to be the number of containments in a longest saturated chain from 0 up to R prime. And we defined the height of an arbitrary ideal to be the smallest among the heights of any of its associated primes. So certainly the smallest height is going to come from one of the minimal primes. Because if I'm looking at an embedded prime, there's another prime living below it, and that's got a smaller height. And then even among minimal primes, they don't all have to have the same height. So let's draw a picture and think about this a bit more geometrically. Not to the best of my knowledge. I hear this just described as, primes realizing the height of I. So example, if we have I is x intersect y comma z, or xy comma xz, then with some orientation of our axes, this is a plane with a line through it. And the plane part, we want to call this variety two-dimensional because we take the dimension of a variety from the largest component. So this component that's the plane, it comes from this prime that only has one variable in it. And so the dimension of the variety coming from a big thing corresponds to the height of the ideal coming from a small thing. Then this xy, this is giving us the plane or the line, and that's not contributing to the height in the same way that we don't think about that line as contributing to the dimension. Examples of embedded primes is a little bit, as we draw these, one can, well, I'll draw a thing and it'll be a little bit of a lie. So if I have x squared comma xy, then up to radical, the radical of this ideal is just the ideal generated by x. And so I'm just getting the y-axis. But also, I have this maximal ideal showing up as also a component, but not a real component, sort of in the topological sense, associated to this variety. And so sometimes people, make the origin fuzzy or something like that. But as a set, this is just the same as if I took radical and said the ideal generated by x. Are there lingering questions about primes and components? Great question. Like I said, I've improved since yesterday. Yeah, and then you get one for an assist. Oh yeah, great. Actually, is it okay if I answer Zach's question and then I come back to you? So, oopsie. Everybody here is minimal. This one realizes, so the height of x realizes the height of I. The height of y comma z does not realize the height of I. This one is embedded, or the radical of this one is embedded. And this is the only minimal prime of J. And what was your question? Yeah. And you want what? Yeah. So if the ideal, great question. The question was, is homogeneity preserved? So if you start with a homogeneous ideal, then all of the associated primes will necessarily be homogeneous. And if you start with a monomial ideal, all of your associated primes will necessarily be monomial. So if in these sort of two ways that are important for us, if you start good, you end good. Great question. Other questions? Yeah. The question was, are the QI uniquely determined? And, oh, watch out. So the ones corresponding to the minimal primes are uniquely determined. For the embedded primary components, you have choices. But the primes are the things that will determine our components, and we'll focus more on, and those are uniquely determined. Good question. Kevin, did you have a question? No. Does someone else up there have a question? No. Okay. So then, back to core Schubert calculus stuff. So where we ended last time was with Knudsen Miller's Annals paper. So the theorem from last time was for W and Sn. And less than an anti-diagonal term order. The Fulton generators of IW form a Grosvenor basis. So in particular, this is telling us that the anti-diagonal initial ideal is radical. So we have a radical monomial ideal. When we take its primary decomposition, we're going to get other monomial ideals. They'll all be prime. And a prime monomial ideal is just generated by variables. So when we look at the prime components of these anti-diagonal initial ideals, we'll just be getting sets of variables. And the next thing we want to think about is what happens with those sets of variables and how do we connect back with other elements of Schubert calculus that we've seen earlier in the week. So well, maybe for this moreover, I think we also need to combine with other people's theorems. So maybe I'll skip that for 1 second. So let's just look at an example that you've done in homework and see if we can recognize these primes as other things we've also seen. So let's consider W is 3, 1, 5, 2, 4. So this was an example that Anna had you do for homework. Then the prime components are Z11, Z12, Z31, Z32. Intersect Z11, Z12, Z23, Z31, Z11, Z12, Z14, Z31, Z11, Z12, Z22, Z23, Z11, Z12, Z14, Z22. So let's maybe draw the locations of these variables. We'll just take the first one. And see if this looks at all familiar to us. So here we have 1, 1, 1, 2, 3, 1, and 3, 2. Maybe I'll do one more. So 1, 1, 1, 2, 2, 3, and 3, 1. So this 3, 2 kind of moved within this little box up along its diagonal. So anyone who still has it, would you pull out the homework that you did for Anna's class where you were looking at this, this particular permutation? And when you were, she asked you to write out, I think, the pipe dreams and the bumpless pipe dreams for this permutation. Does anyone see anything, anyone who doesn't already know this theorem, does anyone see anything that looks familiar to them from Anna's exercises as compared to now? Yes. It looks like where the crossings are. Is it okay if I give you this later? I have no hope. Fair is fair, I promise. Okay, ready? Everyone there ready? That's as close as I'm getting. Great. So the conjecture was that this looks like the crossing tiles. So you had, for example, a bumpless pipe dream that had crossing tiles there. And I'm actually going to go ahead and draw in all of the squiggles. Oh boy, if I can. I have to go there. Then I have to squiggle like that. And the rule is that I squiggle like that. And I squiggle like that. Oh, but now oops, I did this wrong. Sorry. Okay, up, over, that. Great. Nope, that's bumping. Oh, thanks. Thanks. Yeah, let's check. 1, 2, 3, 4, 5. And we're hoping that this comes out 3, 1, 5, 2, 4. Great. Okay. And so this cross here, it can move along this diagonal freely. And kind of once it moves out of the way, shoot. Yeah, it moved out of the way. Oh, there we go. Uh-oh. Once this one moves out of the way, then this cross can start to move up its diagonal. And so these are these ladder moves that Anna showed us for pipe dreams. So those ladder moves are the same things that are happening to the indices in these kind of visual representations of these primes corresponding to this initial ideal of IW. So we have this correspondence between these primes of the initial ideal and pipe dreams. So how do I want to say this? Also, they line up to pipe dreams. And then if we say, let's go ahead and say plus Bergeron Billy, Fomin Kirillov, we're going to get that. So we already knew that these RC graphs, as Bergeron Billy called them, or these pipe dreams, that these give us Schubert polynomials And so from the information that we've seen so far in class, we can go from here to the Schubert polynomial, even if that's historically. So let's go ahead and do that in this example. So actually, this is maybe kind of large. Let's not do this in this example. So you already know how to go from pipe dreams to Schubert polynomials and double Schubert polynomials from Anna. So now you can connect the story and you'll have an opportunity on homework. Yeah, CJ? Yes, yes, yes. Yes, that's the next. Are you ready? So CJ asks, I'd promised that we could get reduced words from this also. How do we do that? So let's go ahead and call this the S1 diagonal and call this the S2 diagonal and call this the S3 diagonal and call this the S4 diagonal. And this is a reasonable thing for us to be doing, to be wanting to care about these diagonals. And the reason is that we've seen these ladder moves. We've seen that we can sort of move freely along these diagonals. So it should be these diagonals that are carrying the information for us. And our rule is that we're going to pick up these SI, or the simple transpositions that we've seen in the intro lectures. And so we're going to pick up these simple transpositions, reading along this way, and then just write them down. So the first thing that we encounter is an S2 there. So we'll write down S2. The next thing that we encounter is this S1 there. So we'll get an S1. The next thing we encounter lives on this S4 diagonal. So this is an S4. And very finally, we see this S3 along that diagonal there. And so we write down an S3. So this is 2, 3, 1, 2, 4, 5, 3, 4. And we'll multiply it out together. So let's see, 1 goes to 2, 2 goes to 3. So 1 goes to 3. Now I'm going to write it as a word so that we can check. Or sorry, as in one-line notation so we can check. 2 goes to 1 and it stays there. 3 goes to 4, 4 goes to 5 and it stays there. 4 goes to 3, 3 goes to 2. And finally, 5 goes to 4 and it stays there. So indeed, we've recovered the permutation that we started with. So these pipe dreams take us between reduced words and these minimal primes and the combinatorics of pipe dreams. So it's a very, very satisfying story. Okay. So the next thing that I want to talk about is multi-degrees. And we'll understand Schubert polynomials and double Schubert polynomials as multi-degrees. And for a single grading, we'll understand degrees geometrically. So then we will, with that machinery in place, we'll go from a Schubert determinantal ideal to its initial ideal. We'll take a sum over the primes in that initial ideal, and we will recover Schubert polynomials in that way. So multi-degrees. Oops. And so 3 options for our gradings, meaning us in this room today. So our 3 options are the standard grading. So that's degree of Zij equals 1 for all ij. The other thing we might consider is degree of Zij equals the ith standard basis vector. So this is going to be a vector in n to the n. into the, I guess, n squared is how many variables we have. Oh, no, that's what we want. This is just taking the rows. And the final option we might consider is if we want to care about rows and columns, then we'll get that the first I of our slots are taken up by the row information, and the next n of our slots are taken up by the column information. So this is an n to the 2n grading. So we computed Hilbert functions, or maybe I should say that this, so this appears in Knudsen-Miller, but you can also see Miller-Sternfels for sort of the textbook version of the information. To see sort of more details than I'll give here. We computed yesterday a bunch of Hilbert functions for the standard grading. And that was just counting monomials that lived in a certain degree that were a basis for a certain part of a vector space. We can do exactly the same thing with whatever grading we like. So for example, with any of these three gradings, we can take S quotient by some ideal that is homogeneous with respect to the grading that we're currently considering. And then we look in that degree, and we see how many monomials have survived that are linearly independent. So we can also compute, just like we computed a Hilbert function yesterday, we can compute a Hilbert function today that's multi-graded. So then instead of needing one variable to index the grading, we'll need a lot of variables to index the grading. So we're still going to have a module. And this t is now either t1 to tn or t1 to 2n, or just t if it's the standard grading. And this is the sum over these k-vector space dimensions. It's an A. As before. So, fact, there exists a polynomial, k of m t, so that this multigraded Hilbert series is equal to polynomial over this kind of standard denominator that depends only on the ring and not on the module. And the mechanics of this we won't really do much, but the important part is that we have this Hilbert series. We roughly know how to compute Hilbert series. This information in a uniform way can be translated to a polynomial. The k polynomial itself, we won't actually study. We're very quickly going to make a change of variables and take a part of it. But other people will care about the whole polynomial, the whole k polynomial later in this course or in talks throughout this couple of weeks, I guess. Oh, thanks, yeah. And who is that? Oh, you know, because I was like twisting some things and maybe I want to allow part of my module to exist in a negative degree. Okay, so here's the thing that we will work with a little bit more. So the multi-degree is the sum of the lowest degree terms of this change of variables or this twist. So we denote the multi-degree by a C. And the upshot of all of this for us is that there is a Hilbert function that we can understand very explicitly, very computationally. You can do it by hand. A computer can do it really quickly. And this is getting us this polynomial here that we're going to want to work with. It has 3 exciting properties. So let's see, do we want to do the 3 properties first, or do we want to talk about degree in the standard graded case and have a picture of it? Second one? Okay, so here are pictures if we are standard graded. Okay, so in this case, the multi-degree is not a vector in n to the n. The multi-degree is a polynomial. This is always true. But the multi-degree in this case will just have 1 t, and it will always be this e times t to the height of I. So from the multi-degree in the standard graded case, we read off immediately the codimension of our variety. And also, we get this nice integer e that is often just called the degree. And the degree means something from a picture standpoint. So, for example, if we again return to our plane with a line through it, then the degree is asking us if we intersect with enough hyperplanes so that we get down to finitely many points of intersection, how many points of intersection do we have? So let's picture this plane with a line through it existing in 3 space. So if I want to intersect with something so that I get down to finitely many points of intersection, I'll probably take a line. In fact, I will. So if I take my plane with a line through it, and I intersect with one other line so that I get finitely many points of intersection, I'm going to get 1 point of intersection. That's going to be the plane and a line going through it somewhere. We're going to assume that I'm not going through the origin, because we want this number to be robust up to small perturbations. So if you have some sort of weird accident where you have one line hitting this sort of smaller codimension thing, we don't want to count that. That's not going to be a count that is sort of stable. And so from this, we see that this degree, if we believe that this means anything, this intersecting count points, this degree doesn't see the line. The degree is only seeing this higher dimensional thing, because my extra line can always be wiggled away from this line going through the plane. So E is number of points of intersection if we intersect, I'm not going to make this precise and just say down until we get to finitely many points of intersection. In a general way. So what this is telling us is that the multi-degree shouldn't be able to see components that are too small. It shouldn't be able to see the primes that are not giving us the height of the ideal. And that is a very general statement. So now are we ready for our 3 good properties? Oh, sorry, was there a question? I wouldn't worry about copying this down. This has no information. But the point is take your variety, throw away the components that are too small, and then intersect with half spaces until you get intersect with something of complementary codimension until you get finitely many points of intersection. Okay. So I'm going to state a very special case of their 3 properties. That's what we want. So suppose that I is radical. So I just want to assume we don't have I want to assume we don't have embedded primes, and I want to assume that each of the minimal primes only appears once. And this is a term order. We have additivity. So this is the multi-degree of S mod I. Is it okay if I drop the T? Anna nodded, so I assume that's everyone says it's okay. Is the sum over these particularly good minimal primes that realize the height. We have degeneration. So this is C of S mod I is equal to, this is the only kind of degeneration we'll think about. So the multi-degree of the ideal we want to study is the same as the multi-degree of its initial ideal. And normalization, which is that the multi-degree of an ideal generated by variables is really easy to read off. That's the upshot of this. I'm just going to say I is some index set. And degree of Z of ij, sorry, now I'm going to dot with the vector t. Okay, so the way that we'll use this is we will want to study a Schubert determinantal ideal. We will degenerate to its antidiagonal initial ideal, which we understand really well and which we have combinatorial models for. We will then read off by summing over all of those primes of the antidiagonal initial ideal, the multi-degree. So let's do a small example. So this is W equals 2143, and less than is antidiagonal. So then we have that the multi-degree of S mod IW is the multi-degree of S mod the initial ideal of IW by degeneration, which is the same as this sum of 4 terms. So S mod Z11, Z13, Z22, sorry, I guess before I want to make this, why don't I just make this a product first? Z13, Z22, Z31. So this is the antidiagonal initial ideal. Let's just sort of check this in this weird box here. So 2, 1, 4, 3. So I have Z11 coming from there. And then this is telling me to take size 3 minors. And so when I take size 3 minors, I'm getting this anti-diagonal here, which is 1, 3, 2, 2, 3, 1. So now I'm taking the sum over Z11, Z13, plus the multi-degree of Z22 plus the multi-degree of S mod Z11, Z31. And these, I'm going to write this down for the n to the 2n grading. And so this is row 1, column 1. I'm going to call my first 3 t variables x's and my second 3 t variables y's to line up to notation we've seen before. And so this is getting me x1 minus y1 times x1 minus y3. Because the multi-degree of 1, 1 is a 1 in my first row, and then a 1 in for my fourth element. And my fourth element is the first y. So this notation of splitting the variables, the first half to be x's, the second half to be y's, is capturing the first half of my multi-grading is EI, and the second half of my multi-grading is contributing the n plus j part. So that's rows and columns splitting into half and half. Then we get x1 minus y1 times x2 minus y2 plus x1 minus y1 times x3 minus y1. And so we've seen this before as the double Schubert, I don't know why this is in quotes, it's already been defined, which is the double Schubert polynomial of W. Yes. That's a great question, which I think I will not answer. So you, one way to think about what I've done is I've taken the isomorphism that sends T123 to X123 and T456 to negative Y1, negative Y2, negative Y3. There are things that I don't really do for which this is more convenient, and I punt to Anna for those. The reason why I make this sign choice in this lecture is because it's the same sign choice that was made earlier in the week. But from my point of view, if I only care about matrix Schubert varieties and their multi-degrees, I would be just as happy to write my Schubert polynomials with a plus. So for me, self-contained within this lecture, it doesn't matter. It would just be an arbitrary and kind of weird choice. Alan. So Alan has geometric reasons for preferring this, coming from, I guess, the conventions that I've chosen, but coming from how we're thinking about the two tori as acting. Truth be told, I don't think about the tori as acting, and so for just this affine perspective, it would be fine, but for other people, it's not. Yes. Excellent question. This is the double Schubert polynomial. What about the Schubert polynomial? What happens if we forget about the columns and we just think about the y's? Well, in that case, sorry, we just think about the x's. In that case, we're just going to set our y's to be 0. And now so with the scratches, we have the single Schubert back? Great question. How about rain check? Great. Yes. Yeah. there are no almond options available. Okay. Is everyone happy with this picture? Happy with the anti-diagonal story? It's really great. We have this happy marriage of the combinatorics and the algebra and the geometry that other people can comment on. So this story is very pleasant and well controlled. And now for something completely different. We have I'm just going to talk about vertex decomposition of a simplicial complex and the way that this connects to the story that we've just seen. I won't really say much about, but these anti-diagonal initial ideals give rise to subword complexes. Subword complexes are vertex decomposable. So things that we will see in this next section do connect back, but I won't say much about it. I'll use it in a slightly different setting. So a simplicial complex delta on some vertex set, I'll just call capital N, is a set of subsets of N that is closed undertaking subsets. So if I have 1, 2, 3, I have to have 1 and 2, 1 and 3, 2 and 3. I also have to have 1, 2, 3, and I always have to have the empty set. And so this is the set of integers from 1 to capital N. So the same way that Frank defined it. Ready, CJ? But we can choose the set to be whatever we want. So this is just, for me, some set of integers. So the elements of delta are called faces. Those not contained in any other face, properly contained, that is. Maybe that's what other means. Are called facets. So here's an example. So delta is going to be one, 2, 3, 4, 5. So this set, in this case, capital N is 5. And the facets are 1, 2, 3, 2, 3, 4, 3, 4, 5, and that's it. And once I tell you the facets, you know how to get the rest of the faces, but you're just going to take subsets of the facets, and all of those have to be in the complex. There's this thing called the Stanley-Reisner correspondence. And here's how we're going to get back to some commutative algebra. There's a correspondence between simplicial complexes on N and square-free monomial ideals in K adjoin x1 to xn. And here's how the correspondence goes. If mu equals xi1 up to xit, let's say t is not in use, then, so if this is in my square-free monomial ideal, then I1 up to IT is not a face of delta. So let's go back to this example here and make the square-free initial ideal for it. So now delta as above. I delta, it's enough for me to write as generators the minimal non-faces. So x1, x4 is not a face of this complex. x1, x5 is not a face of this complex. x2, x5 is not a face of this complex, and so it's a generator of my ideal. What questions are there about this construction? Yes. No, this is fine over any field. Any other questions? Yeah, Alan? It sounds from the laugh like that made it to the room, but I guess for the benefit of the recording, Alan says that some people take the convention that that x1 through xn have to correspond to, every vertex has to be in your simplicial complex. And Alan further comments that that convention is wrong. I'm inclined to agree with Alan. Other questions, comments, concerns, complaints, dropouts? Okay. So CJ asks, how do I know that it's enough to consider the minimal non-faces? And so I'm going to leave that, I think, as an exercise. I think you'll be able to convince yourself pretty quickly that that's enough. Okay, so I want to look again at this ideal and these facets and also consider a prime decomposition. So a prime decomposition of this ideal is x1, x5 intersect, so it's 1, 5. I'm going to, maybe I'll say the punchline aloud and then I can get the prime decomposition more quickly. So the complements of the facets give me the minimal primes of the ideal. So one of my facets is 1, 2, 3. Excluded from 1, 2, 3 is 4 and 5. So that tells me that x4, x5 is a prime corresponding to I delta. Another facet is 2, 3, 4. 2, 3, 4 excludes 1 and 5, and so x1, x5 is a minimal prime of I delta. And finally, 3, 4, 5 is a facet. This excludes 1 and 2, and x1, x2 is a minimal prime of I delta. Square-free monomial ideals are radical, so they do not have embedded primes. They also do not have primes that sort of show up more than once. It is not required that all of the primes have the same height. The reason that these primes all have the same height, meaning all have 2 generators, is that all of the facets were the same size. Because all the facets were the same size, they left out the same number of elements. So all facets are the same size is the same information as all minimal primes of I delta have the same height. And this is the same information as the variety of I delta is equidimensional. And equidimensional will be a little bit attractive to us because we want to be computing these multi-degrees, and multi-degrees like to select primes that are the right height for the ideal. And so when we're equidimensional, we don't have anything to throw away. All of our primes are actually contributing. We're going to call this in all cases pure. It is very standard to call the simplicial complex pure. It's a little bit less standard to call the things on the algebra geometry side of the equation pure, but we will this week. Okay, so from this ideal, from this simplicial complex, we're going to form two other simplicial complexes. And the reason for forming these simplicial complexes is to be able to work inductively in something that is smaller and still good. So from delta, the deletion denoted this week, del 5, is exactly what you would think it would be. It's if we take the simplicial complex and we just delete 5. And if I don't have 5, I can't have an edge 4, 5, and I certainly can't have a triangle 3, 4, 5. So I'm just going to delete. The link is going to be a little bit more mysterious, though, algebraically a little bit better in certain ways. The link, is going to be everything in the deletion. We start with the deletion. Everything that I can join up with 5 to make a face of delta, not including 5 itself. So 4, 5 is in my deletion because 3, 4, 5 is a face of delta. 4 is in my link because 4, 5 is a face of delta. 3 is in my link because 3, 5 is a face of delta. The empty set's everywhere. So let's think very quickly about how we can get these ideals of these new simplicial complexes directly from the ideal of I delta, and that will set the stage for something we'll do tomorrow called geometric vertex decomposition. So if I want to get the ideal of the deletion, then what I'm saying is that 5 is no longer in my complex. And so if 5 is not in my complex, 5 had better be in my ideal. Because like Alan told us, it's really important to allow vertices to not necessarily be written down, even if they're in the ambient set. So the ideal of this link is what I get just by adding 5 into my complex. Once I add, or into my ideal. Once I add 5 into my ideal, I don't need these generators that have a 5. Oops, sorry, thank you, this is deletion. Who asked that? Just in time.